All right, hello everyone. Welcome to the first part of the video for section 4.8. Yes, we're skipping over section 4.7 for right now. We will come back to it. I would suggest, however, that it might be a good idea to look ahead a little bit at 4.7 already. Those are what we call applied optimization problems, and there's some really challenging ones in that problem set, so it would be a good idea to start looking at it now. Okay, so on section 4.8, we're going to look at something called L'Hopital's rule. And I'll tell you right now, there's always a mystery about this name. So here you see that I've got it as L'Hopital with a bunch of accents and other things in it. Sometimes you see it spelled like this, which I could look it up, I suppose, but I can never remember if that's a misspelling or just there's some uncertainty about the spelling. But the point is this, if we read it in English, looks like La Hospital, and I promise you right now that is not how this is pronounced. This is not the hospital rule we're learning about. It's called L'Hopital's rule. And it relates to limits. So you remember way back at the beginning of this whole calculus adventure, we started looking at limits. They were something that helped us then later understand finding the slopes of tangent lines, which eventually led to derivatives. But let's look at this. So we're given this limit as x approaches 0 of sine of x over x, and we want to try to evaluate it without using a calculator. And let's first of all figure out why we would have to avoid using, so it says we don't need to use a calculator, but that must mean that there must be some challenge about finding the limit here. So limit as x approaches 0 of the sine of x over x, and yes, I just rewrote the whole thing. I'm not sure why I did that. One thing we could try here is to plug in 0 into both the function in the numerator, function in the denominator, because it's in the domain of both of those. But notice when we do that, okay, first of all, we get 0 in the denominator, which we already know is a problem. And then what is sine of 0 equal to? Well, we've got to think about in radians. 0 is over there on the right, and the unit circle, and the value there is, oh, right, it is also 0. So what we've got here is 0 over 0, which is not only a problem because there's a 0 in the denominator, but 0 over 0, we can't just cancel those out and make that 1. That's an even more kind of undefined term. So what are we going to do instead? Well, for this limit, I am going to call this top function here, the sine of x, I'm going to call that f of x. I'm going to call the bottom function there x, g of x. Okay, just give them names. And we just saw just a second ago that f of 0 being sine of 0 is 0, and g of 0 is also equal to 0. And I'm going to use that. I'm going to rewrite this limit here. So I'm going to take this move it over to here. So I'm going to write this limit as the limit as x goes to 0 of sine of x minus 0 over x minus 0. Okay, and notice that's a totally valid thing to do because subtracting 0 from both the top and the bottom, that doesn't change the value of each. Sine of x minus 0 is still sine, and x minus 0 is still x, so we didn't change any values there. And then notice that in the case of both of these functions, these two things right here are equal to the value of the function evaluated at 0. So that tells me I can rewrite this limit now as the limit as x goes to 0 of sine of x minus f of 0 over x minus g of 0. Okay. All right. Next thing. And this might seem like a little math magic, but I promise you there's nothing up my sleeves, even though you can't see my sleeves right now. Okay, so I'm going to do the limit as x goes to 0 for both of these, the numerator and the denominator. I'm going to divide them both by x minus 0. Is that what I want to do? Yes, it is. And so we'll have on the bottom here x minus g of 0 all over x minus 0. And I'll rewrite this one more time. So the limit as x approaches 0. Instead of sine of x here, I'm going to write f of x minus f of 0 over x minus 0. All divided by, instead of x, I'm going to write g of x minus g of 0. And then take that divided by x minus 0. And from there, now, what can we do? So recall that when you have a limit of a stuff in a fraction, you can break that into the limit of the top over the limit of the bottom. So we can do the limit as x approaches 0 of f of x minus f of 0 over x minus 0. We can do that over the limit as x approaches 0 of g of x minus g of 0 over x minus 0. And we need to think about what each of those things is equal to. And I'm going to go ahead and rewrite this top one as f of 0 plus x minus f of 0 over 0 plus x minus 0. So notice those are still the same because 0 plus x is still just x. So the stuff I highlighted in blue there on the right is not any different than what's from the left. And here's the moral of the story on this part, is what we have here now, this f of 0 plus x minus f of 0 over 0 plus x minus 0. Hopefully you recognize that looks very similar to our limit definition of the derivative. So if you remember back from the beginning of chapter 3, our limit definition of our derivative was the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x, right? And I know what we have here is not exactly the same, but hopefully you would agree with me that it looks like a similar form. And so what that tells us then is that this top limit, using the f's there, that's equal to the derivative of f. And because we see we have these f's of 0 and 0 here, it's actually the derivative of f evaluated at 0. And we could go through a similar argument and show that the bottom here is the derivative of g evaluated at 0. Okay, so what we've done, I know there's a lot of stuff here on the screen, but I'm going to write up here equal to my limit is we've showed that it is the same as f prime of 0 over g prime of 0. Okay. All right, so that was a lot. I know we just went through, and I will tell you now that is not something I would ask you to do on a quiz or an exam. That was just one of those things to help us understand where formulas come from. So we see now that we can find this limit by just taking the derivative of the top, evaluating it at 0, and derivative of the bottom, and evaluating that at 0. So if we take the derivative of the top, f prime of x, derivative of sine is cosine, and then f prime of 0, in this case, would be cosine of 0, which is just positive 1. Derivative of the bottom Using the power rule would just be 1, so g prime of 0 in this case would just be 1. So we have f prime of 0 is 1 over g prime of 0 is 1, so we get 1 as our final answer for our limit there. Okay? All right. So what we just used, or what we just learned about that, is L'Hopital's rule. So here is how it works. Is we have two functions that are differentiable, and the limit of one is the value of x, or as the value of the inputs approach a particular value is 0, and the value of the other as the inputs approach a particular value is 0. Then the limit, as the inputs approach that value, of f of x over g of x, or of the first function over the second function, is the same as the limit of the derivative of the top divided by the derivative of the bottom. Okay? And that is, as you can see, really what that is, because these two limits here equal to 0, is just like on the one we just saw. What we saw is that this derivative, or this limit here, the limit we started with, gives us a 0 over 0. Okay? And that 0 over 0 is one of what we call our indeterminate forms. Determinate forms. Okay, and if you're trying to copy that down, the first word there is spelled indeterminate, indeterminate. All right, similarly, if we have a similar setup, we're taking the limit of the ratio of two functions, and the limit of the top thing is equal to positive or negative infinity, and the limit of the bottom thing is equal to positive or negative infinity. Well, that's one of our another indeterminate form that we're calling an infinity over infinity case, and we can do a similar thing. Take the derivative of the top function, the bottom function, and then find those limits. Okay, so let's look at an example of this, or another example, I should say. So notice here we have the limit as x approaches infinity of e to the x over x. And if you think about, we could take each of these limits separately. So if you look at just the top, if the values of x are going towards positive infinity, if you think about the graph of e to the x there, it's just going to keep growing larger and larger. So that would also be infinity. And similarly here with the bottom one, as x grows bigger and bigger towards infinity, if our function is just x, that will also grow towards infinity. And so notice here is where we get one of our indeterminate forms. We have infinity over infinity. So that tells us now we can use L'Hopital's rule. So what we'll do is go ahead and rewrite the limit, but this time we will take the derivative of the top and the bottom. So we take the derivative of the top, derivative of e to the x, we know is just e to the x. Derivative of the bottom, derivative of x is just 1. So we have the limit as x approaches infinity of e to the x over 1, which can reduce to be limit as x goes to infinity of e to the x, which we just found that out. We already know that that is infinity, and that is our final answer. Okay? And that's okay. We got the answer infinity. Remember, that is not an indeterminate form. An indeterminate form is one of those 0 over zeros, or positive infinity over negative infinity, or negative infinity over positive infinity, something like that. All right. Great. That's all for now. Thank you for watching.